So in a communication system, there's multiple elements that can actually affect what we receive. We start with the data, and then we put it through a transmitter, and then we have a channel that it transmits over, and then we have a receiver. And so the question is, where is the error introduced? And the answer is just about everywhere, in the transmitter, in the channel, and in the receiver. So let's talk a little bit about signal quality. Signal impairment could be due to random noise or distortion. And I should point out here that there is a third category that we've talked about, and that is with an interferer. And I just want to highlight that random noise is typically thermal. Distortion comes from our circuits, and an interferer comes from the environment. And I point this out because oftentimes we look at a received signal and we call anything that we don't want simply as noise. And it's really important that you separate the concept of random noise from the concepts of distortion and interferers. These impairments can be reduced but cannot be removed completely. Note that an amplitude loss is not an impairment. And this is something that I think is a little bit counterintuitive initially. We think about the problem with a received signal might be that it's so small. But it turns out that we can amplify signals that are really, really small. A cell phone can actually pick up picowatts of power. The real limitation in amplifying a signal is what is the noise or the distortion or the interferes, and how do they affect our ability to amplify. Because if we had a noiseless environment with no interferers and no nonlinearity distortion, we could simply almost at infinity amplify any signal and get a signal that's large enough to use. So it's not about the small signal, it's about the noise, the distortion, and the interferers that are a problem. And one note here is that if we have linear distortion, and linear distortion, for instance, might be, we might have a channel that has a delay based upon frequency, or we might actually have a filter that's in there. And basically, if we know how each frequency component is treated, and they're all treated identically, meaning a small amplitude or a large amplitude at a certain frequency gets the same treatment, we can actually fix this with something called equalization. Because remember, nonlinearity is really the concept of if I put a small signal in a system, and I'll just draw that here. If I have a small signal and it goes into a box, and I get a certain output, and then I put in a very large signal, if that large signal doesn't come out with exactly the same transfer function as the small signal, that means I have a nonlinearity there. And equalization means if I have a linear transfer function, I can undo it. What I can't do is undo nonlinearity, except in a few advanced architectures where I can try to pre-distort signals to compensate for it. But I just wanted to separate the concepts there, that linear distortion is actually something we can handle relatively easy, and we do. Nonlinear is really the problem. So in order to quantify the impairment, we compare the power in the useful signal, that's a signal we want, to the power in the imperfections. And so one metric is the signal to noise plus distortion power. And so here is what we want. Here is the thermal noise, and here is any distortion that we have. It turns out, however, that oftentimes we can't separate these two, or it's hard to separate these two in a measurement. And so what we do is we just lump them all into a noise power, and we define the signal to noise ratio as the power of the signal to the power of the noise. And as you can see, because this is a ratio, we're going to express this typically in terms of dB. But remember, the actual signals, the actual powers, have a linear representation. So when you're doing your mathematics and calculations, you'll oftentimes be dealing with the linear version of the actual power and noise, and then you can take the ratio, which is still a linear quantity, and then if you want to express it in dB, you can do 10 log of that to give you the signal-to-noise ratio in dB. So just remembering that all of our signals can be treated as linear, or if it's a ratio, as dB. So let's talk a little bit about the detector in a receiver. There's always some error in detection, and the probability of error indicates the rate at which an error might occur. PE is often stated as bit error rate, BER, or symbol error rate. And it's pretty easy just from the words to figure out what these are. The bit error rate is how many bits are incorrect, and symbol error rate is just how many symbols. And remember that we have 2 to the k, where k is the bits symbols. So remember m is equal to the k, where k is our bits and m is our number of symbols. And just to give you an example, a bit error rate of 10 to the minus 8 means that in every, let's see if I can get this correct, every 100 million bits detected, 1 bit may be estimated incorrectly. And just to give you a perspective, 10 to the minus 8 is typically a decent bit error rate. Systems do much better. Bit error rates as low as are mathematically as high as maybe 10 to the minus 4, 10 to the minus 3 might be okay in some low quality systems. But you should really get in your mind that 10 to the minus 5th to 10 to the minus 10 is really an area where we try to get our bit error rate. So we do try to get the error down very low. And oftentimes we have to do this with error correction. It's not simply coming out of our received signal. And so let's talk a little bit about a receiver design. Coming into our receiver is the signal plus noise. And so there's a signal to noise ratio at the input to our receiver. And then we've got a receiver chain, and at the end we're going to put a detector. And that detector is going to see a certain signal to noise ratio out of the receiver. And the question is, are these two the same? What do you think? Unless this is perfectly ideal, probably not. Also shown here in the box that typically we look for a desired signal to noise ratio to give us a bit error rate. And I'm going to show you how to link these two in just a minute. So bit error rate versus signal to noise ratio. So the bit error rate depends upon the signal to noise ratio of the received signal. So if here is our input to our receiver, after our receiver, this is the received signal. And the detector will detect it, and the bit error rate will depend upon what this SNR is. And remember, we have an SNR here, and these two are not equal unless we had a perfectly ideal receiver. And one comment that we'll see in just a second is that we've talked about on-off key and 4 QAM and 16 QAM and 64. All of these higher order modulation schemes require a higher signal to noise ratio. And that makes sense because all along we've talked about if we have 4 QAM, we have 4 points. And then if we go to 16 QAM, we add more points. But what I've done just here is I've actually increased the overall power so that I can have the same spacing between my points. What we'd really like to do is we'd really like to go in, and if here's our 4 QAM system, we'd like to transmit the same power. So that means when we go to 16 QAM, we're actually doing this. And so it's easy to see that the spacing between symbols gets much smaller, and you can see intuitively that we're going to need a better signal-to-noise ratio in order to be able to discern those different symbols. And we mentioned throughout this, it's not really covered in the course, but error correction is something that really helps the bit error rate. And in fact, most radios today would have a horrible bit error rate if it wasn't for error correction. And ways we can do that is we can, for instance, do a mathematical algorithm on a set of bits at the transmitter, and we can send those bits and send the key to that algorithm to the receiver, and then the receiver receives the bits and then looks at the key. And if it gets an error in one of the bits, it can look at the key and say, ah, this isn't the correct signal. Let me try to figure out what it should be to give me that key. And once it figures that out, it's reconstructed the original signal. And so that's a simple way of looking at error correction. And here's a really nice graph. And what we have on the left here is symbol error rate. I could have also put in here bit error rate. It would just change the numbers a little bit. And you can see that we have different modulation schemes. We have QPSK, 16 QAM, 64 QAM. And here is the signal to noise ratio. And these curves actually come from a bit of complicated math having to do with the probability of errors and the intersymbol spacing. But you can get a set of curves, and they're pretty much standard for each modulation scheme. So you can go look these up. And what you can see is that for QPSK, for a bit error rate here at this line, we only need maybe 11 dB of signal to noise. If I want to go to 16 QAM, then I'm out here at 17. If I want to go to 64, I'm almost at 25. I'm almost at 31 to go to 256 and so forth. So you can see basically from this curve, to keep a standard bit error rate, each modulation scheme is going to need a higher signal to noise ratio. And as I said, that makes sense because typically we're transmitting with a constant power. So as we go to higher order modulations, our symbols are closer together, and therefore we need a higher signal to noise ratio to be able to receive. So if somebody came to you and wanted you to figure out what the bit error rate of your system could be, you could actually just take your modulation scheme, figure out your signal to noise ratio, and find one of these charts, and it would tell you what your bit error rate could be. Doesn't mean you'll actually be there. Typically, an actual system will operate somewhere on this side of the curve. And that makes sense because there'll be other non-idealities that'll help require us to have a higher signal to noise ratio in order to receive our signals and get a certain bit error rate.